All right, so hi, thank you for listening in to my JTD. I'm going to be talking about NVMe Hotplug. So this is a project that I've been working on for all of 2019 and a little bit before that. So I'm excited to share the work that's going on, which is pretty close to integrating at this point, and just talk about some lessons learned. Can everyone see my screen? It looks like I can see it. Now whether I can go to the next slide. All right. So this is Hotplug depicted with a fire and a plug. And pretty accurate representation of how it feels sometimes working on it, but it's a lot of fun. So I'm going to talk about the motivation for the project, some high-level goals, the strategy that I took to kind of tackle different things, some implementation details, and I'll talk through a couple of the big bugs that were fixed. And then we'll have some demos. They're very clear, squarely systems demos, but it'll be exciting nonetheless. So first, why NVMe? So if you've heard of NVMe, it's probably in the context of NVMe SSDs. But the standard itself, so NVMe is a standard. It refers to non-volatile memory, specifically storage over PCIe, which is another standard for adding hardware devices to a system. It's used for lots of stuff, NICs, graphics, storage, etc. And the specification is designed for more for NVM instead of spinning disks. So that means things like more I/O queues and queues that are much deeper, which are more optimal for those types of drives. And like I mentioned, there are several form factors, but we're primarily interested in Joyent and people purchasing hardware. And the U.2 form factors, which are 2.5-inch hard drives. So that is basically the same size as the disks we already use physically. And we already have driver support, so this project was more about kind of operationally improving Hotplug. And so what is Hotplug, and why do we care about it? So Hotplug is a pretty broad term, but it basically means adding and removing devices from a live system. And that can be a couple different types. We have more coordinated Hotplug, which is where you tell the operating system, like, I would like to remove this device, please clean up after it, and then I will remove it. And then surprise, where you just walk up and pull from the server and hope that works. And so both of these are important. And Hotplug itself provides a lot of operational gains because obviously you don't have to power off the system because it's a live system. And also I found that just doing work in this area will harden the system quite a bit against panics and errors if you accidentally pulled the wrong device, just because if you support surprise removal and you pull the wrong thing, you might have some other errors upstack, but at least you're not going to panic. So it's some pretty good gains, I think. So here's a depiction of the hardware I've been working on, or rather a small part of it. So this is a server in the SF lab, and there are 4 NVMe drives, and that second one from the front I've been abusing a lot. And so on the right side, you can see how when it's pulled, there's no LED. Obviously, it's not all the way out of the slot, but that's enough for the system to not be able to use it anymore. Okay, so the project goals. So I mentioned coordinated and surprise Hotplug. And so this project is oriented around NVMe SSDs because we would like to be able to really use those in the field. So caring both about coordinated insertion and removal and also surprise removal. And then there's a couple different axes that you could remove things or other parameters on these as well. So if you have a drive in a Z pool versus not in a Z pool, how do those two scenarios differ? And perhaps with ongoing I/O to the disk and without ongoing I/O, and making sure all these different kind of scenarios work. And so the way that kind of went about this project was that there already was Hotplug support in the operating system. There was this huge framework that was integrated 10 years ago with a bunch of different things in it, tooling, PCIe support, lots of stuff existed. But it wasn't really clear how much of it worked in different scenarios. So I basically just tried, pulling a drive in a Z pool or pulling a drive with I/O and kind of seeing what happened, and hit a bunch of different problems and just kind of iterated on those until I was done. And so first, talking about coordinated removal insertion. This is kind of where I started because it was seemingly a lot easier. And that mostly worked from the start with a couple bugs referenced down at the bottom. But it was mostly fine and it was pretty quick to get through. So these commands here are config-ADM, which is this command line tool. I guess it's like configure administration, I think, if you wanted to flesh it out in your head a little bit. And it takes commands that you can use to manage connections, among other things. And so this first command is saying unconfigure the item in slot whatever the argument is. And that means offline the device. So detach its drivers, clean up the /devices file system, do all the normal cleanup you would do when you take out a device. Kind of a little bit further step would be to disconnect the slot, which means do the unconfigure step, but then also power it off. And then for going the other way, if you have an inserted drive, you can connect to power on the slot with the drive in it, and then configure it to online the device. And again, these things mostly already worked, and I'll show config-ADM in the demo so you can kind of see what it looks like a bit later. So here's a couple experiments that didn't go so well. The first one I tried was to just remove the device and plug it back in. Not in a Z pool, not doing any I/O, just taking a drive from the system and plugging it back in. And what was pretty strange was that we didn't see the driver detach when it was pulled, which is what you would want as a part of this project. But then when it was plugged back in, it would detach, which was pretty backwards. So that was strange. And then these next two are kind of similar pathologies, but for different scenarios. So I tried running DD on one of the NVMe disks and then pulled it in a surprise removal scenario, and it just DD would hang in the kernel, so it's unkillable, just waiting for that I/O to come back. And obviously, it's not going to come back. The device is gone, so something needs to tell DD to wake up and exit. And then another one was sort of similar, but no necessarily ongoing I/O, was having a device that was just in a Z pool, pulling it, and then I tried to run Z pool status to see what the status of the pool was, and it was also hung trying to talk to that disk again. So nothing ever told it that the disk was gone, or otherwise, why would it be talking to it? So I'm going to go through how these three big bugs were kind of fixed, and I'm going to start with the first one. So again, removing the device, plugging it back in, and seeing that the detach happens when it doesn't happen when it's pulled, but when it's plugged back in. So to understand this, we need to look a little bit into the Hotplug framework I mentioned earlier. And so this is a state machine representing the state of connections on the system. And so a connection refers to any physical place that you would do Hotplug. So a PCIe slot, for instance, it was the thing I carry right here. And so the states that we can talk about are empty, which means there's no device there, it's just an empty slot. Present, there's a device there. Powered, there's a device and the slot is powered on. And then enabled is a little bit more general, but it basically means device is ready to have I/O to it. So it'll have its drivers, /devices, WFS, all that. So this is not a strict state machine in that it can only move along these edges, but it does kind of represent the order of operations you might want to think about when you're thinking about onlining a device from an empty state. So what was happening in the removal case when I didn't see the detach when it was pulled? So after some debugging, I found that the way that this status change was, the state was changing here, was that the PCIe bridge, which sits in front of the slot and is the one that is listening for PCIe related interrupts for that slot, receives a PCIe Hotplug interrupt, which is a specific type of interrupt in the PCIe specification for things like Hotplug, indicating that the status of the slot had changed. So it had gone from having a device present to empty. And so this would get sent over to the Hotplug framework, and it would try to request a state change for the slot to be empty from the interrupt path, which makes sense because it's now empty. But then the state change handler, which was in another thread, would go fetch the state again from the hardware, and again, reading from that same state that the interrupt came from, and see that that connection was empty and then just do nothing. So its kind of internal state about the slot was out of sync because it was receiving the status through an interrupt instead of through, say, a config ADM in a coordinated scenario where all state requests will come to the Hotplug framework first before actually making any changes to the hardware. So that was straightforward enough. And then the insertion case is even weirder. So recall that I said there was a detach after the pull was inserted. So the NVMe driver detaches when it's plugged back in. And so what was happening here was that that bridge got the interrupt, as before, saying the slot status had changed. And the Hotplug code would say, now there's a device present, please change this to present. And the handler would go get the state again and see that it is present. And because it had never heard of any state changes prior to this, it assumes, oh, this must already be enabled, because enabled is not a state in PCIe the way present and empty are. So it just assumes that it already has everything and then sets the state to enabled. But then when it actually goes to check to see what to do about it, it sees it's going from enabled to present, which is backward in that state machine. And it detaches all the drivers because it thinks it doesn't need them anymore. So that's really odd, but it all makes sense when you think about it from a coordinator removal scenario where there's no side door coming in from the interrupt path of device changing. So the solution for this was to kind of work on those state change transition checks in the framework to be more aware of hot removal and make smarter decisions when the states seem kind of out of sync. And when in doubt, just to clean up structure. So if we get an interrupt now that says the slot is empty, just clean everything up, or at least try to, because we don't want to leak, drivers or have things hanging around for a device that isn't there. All right, so the next two that I mentioned were both related to I/O hangs. And so what was going on here was that they were both DD and ZFS were not being notified that the disk was gone. And so I'll talk about the DD case first. So it seems like it's really best for the NVMe driver to be the thing notified that a device is gone when it comes to I/O, because it knows what threads are waiting for I/O, it knows what commands it has. And so there's this interface that was a part of the Hotplug framework called NDI, Nexus Driver Interface. A Nexus driver, by the way, is any driver that enumerates children. So you can think of drivers as a tree on the system. And at the very top, we have the root. And then beneath, like the PCIe bridge, for instance, is the NVMe driver, and then a block dev driver. And I have a depiction of that on the next slide, so you can kind of get a sense of what that looks like. But basically, Nexus drivers have children, and they know things about their children that maybe the children themselves can't always know, and are responsible for managing that in some ways. So I added support to the Nexus driver of NVMe to start firing removal events, and also adding a callback handler to the NVMe driver to fire and removal events so that it can, for instance, fail I/O and clean up, fail all new opens and ioctals and things like that, so that anyone that tries to use it will know that this device is gone, or at least get an error. And so here's part of the driver tree, like I was mentioning on the last slide. So root nexus is the root of the whole tree. It's basically just the root is its purpose. And then underneath that, we would have MPE, which is the Nexus PCIe driver for x86. And then beneath that, there's a PCIe bridge driver, which was the one that was getting the interrupt about the state change. And it calls into this Hotplug controller, which is part of the Hotplug framework, which helps manage some of the Hotplug-related interrupts and things like that. And then the NVMe driver, which implements the specification for NVMe and sends out commands. And then block dev, which is a generic block-oriented device driver for non-volatile memory. So that does a little bit more of the work for like the block dev parts of I/O outside of the NVMe spec. And so to fix or to add support for the event generation, I added a new BusOp, which is a Nexus driver operations vector for NDI events. And so events, when they happen, are passed up the tree until a Nexus driver can handle them. So it's important to pick the right spot to do that. An NPE is a good case because usually a bridge, or at least in the case of NVMe, will only have one device under it. And so it makes a lot more sense to generate removal events one tree higher so it can manage all PCIe devices. And then the NVMe driver adds this callback when it attaches, and when it gets the remove, it will mark itself as dead and fail outstanding commands. And now we have a demo. So to do this, right now Cody Mello is in the lab, and he's gonna do some surprise removal for me as an operator. But we're gonna start with coordinated removal. And I have the commands kind of written up in the slide so you can, sorry, I'm moving some windows around, so that you can review them later if you want. But I'm gonna do it all here. So this is, I'm on NVMe, which is the name of the actual system, which is convenient, easy to remember. So this is config.adm, and when you run it by itself, it'll just list all of the connections on the system. And so if you look up toward the top, you can see there are 4 NVMe drives, the ones that were in that picture earlier. Slot 1, slot 12, PCIe 8, PCIe 10. And they're all connected, which means they're powered on. Their occupant is configured, which that's the actual drive itself. So they're all online, they're ready to use. So if I want to coordinate removal, say, of one of these, also I'm going to run a little dtrace that just traces the return of NVMe attach and NVMe detach, so that you can just see when that happens as a metric of things working. Sorry, I'm zooming in a little bit. One more thing before I do that, if we go into MDB, there's a command called prtconf, :prtconf, which prints the device or dev info tree. And if I give it the name of a driver, so in this case NVMe, it'll tell me how many, or show all the instances on the system. And so we see 4, which makes sense because there are 4 disks. So that's just another good way to check that instances are attached or detached. Okay, so if I do an unconfigure of the disk in slot 12, which was that second disk pulled in the slide, it's going to take a few seconds because this code is not very fast. But we see this detach fire over here. If I look at it in config.adm, we're going to see that it's still connected, so it's still powered on, but the occupant is unconfigured. And if I go back to MDB, we're going to see that there's only 3 instances now. So that seems to work okay. So let's online it again. We see it attach. Cool. I could also do a disconnect, but that would just power it off. So I'm going to go to the surprise removal part now, which is a little more fun. Oops, sorry. Cool. So I have 2 disks in a Z pool called test. Uh-oh. Sorry, I'm not sure why that happened. Let me try onlining it. All right, so we have them in a Z pool. And now I'm gonna go to the file system, and just the /test file system of that pool, and just echo some data into a file. Just see that there's stuff there. And now I think, Cody, if you're ready, you can go ahead and pull it. I can't tell if you pulled it yet. Sorry, this is a little exciting. All right, I see the detach. Great. So if we go back to the status of the Z pool, we see that it's degraded, which makes sense because it's from this is the disk that was removed. But we can just make sure that we can still read the data, maybe write some more. Cool. All right, so I think Cody can plug it back in now. And I'm going to watch the console to see when it's plugged back in so that I can tell. All right, see it inserted, this message. And now I'm going to bring it back online. So one thing that I didn't really talk about was auto onlining of disks, which is something we chose not to prioritize because you can manually online them when they're plugged back in. it's not always clear that you would want to auto online anything that you plug into your server, but that is something worth exploring at some point. So now let's check the Z pool status again. Still degraded. That's unfortunate. We've seen an issue like related to when I do the DD demo I'm going to do, where sometimes it doesn't detach. So I suspect that might be related here, which I have a ticket for. All right, so we've got our Z pool back. Now I'm going to do something sort of weird and just DD directly to the disk, even though it's in the Z pool, but just to demonstrate that part of the change. So I'm just getting the command. This is a really fly by the pants demo a little bit. Apologize for that. All right. So I'm going to start this DD. This is the same disk that he's been pulling. And we see it's getting I/O. All right, Cody, you can go ahead and pull it. And we're going to see it, hopefully, there we go, exit with an I/O error. So that is coming from that remove callback I talked about earlier. So that is the live demo. And I'm going to quickly talk about some remaining work. So the code I've worked on is in review. Hopefully we'll integrate pretty soon. And then there's a few other issues that are still existing. If you're curious of taking a look at any of them. If you remove a disk from a Z pool, that has ongoing I/O. So similar to the DD case, but with a Z pool I/O. It will panic due to an existing bug. And so that's linked there. Earlier during the live demo, I mentioned there was a problem sometimes where the driver would not detach after that DD test because BlockDev will still have references to it. So that's another issue. Disk info is kind of weird with NVMe drives. Sometimes it won't list all of them. And then I mentioned auto onlining devices when we insert a disk. And then there's a lot more work to improve NVMe operationally, which Robert sent out an email about in August. So if you're curious about any of that, I would check the email out. And I think that is it. Does anyone have any questions? I'll check chat too. All right, going once.
Hey.
Yeah.
Isn't there a NVMe management interface, I think it's called, or it's like NVMe IF or NVMe MF or something like that?
Yeah, there's NVMe ADM. I haven't used that too much since most of what I was doing was just toggling the device state. But there is, I believe, there's a man page for it, at least a help message.
Oh, I'm referring to it's an actual management spec like enclosure services.
There's the NVMe management specification. There is.
Yeah,
I'm sorry.
That's kind of separate from this stuff.
Okay.
And it was kind of formalized with a little bit of 1.2, 1.3. It mostly provides a sideband channel over I2C to kind of get at a bunch of the drives information.
Right. Okay. So this is completely different from that. Okay, cool. I mean,
Yeah. That's kind of more of like a SES-like thing.
Right.
Kind of because the enclosure services or like lighting LEDs doesn't really end up interacting much with the surprise removal case, because once you've pulled out the drive, it's no longer connected to the I2C.
Right. Okay. I was just wondering if this work involved any of that, but no. This is cool by itself. This is super helpful for operations, indeed. So.
That's great to hear. Any other questions? Sorry, I haven't really been looking at chat since I was sharing my screen.
What was the most interesting thing you discovered while doing all this?
Well, there was a really fun firmware bug. I didn't put that in the presentation because I wanted it to be able to go on YouTube, and I wasn't sure that would be allowed. But I can link that ticket. But we basically found that when I have to look at the details to remember exactly, but basically if we pulled one disk, another one would report that it had been powered off, I think, even though it was still powered on. So that was pretty odd. It was also pretty fun to kind of learn about this framework that was integrated a decade ago, because it seems to have really been is designed for general Hotplug support for different types of buses or like Nexus drivers, but it was a lot of support specifically for PCIe, so that made it very convenient since NVMe is over PCIe, and I didn't have to do very much work on that front. So that was really cool to learn about too. And that ticket I'm going to put in chat if no one has yet about the firmware bug. Does anyone else have any questions? Okay, thanks everyone.
Thank you.